without a doubt, for what it's worth. So what I want to do first is, having seen these presentations and seen what your classmates had done, what kinds of general conclusions might we come to? So in particular, I hope you all noticed that in some presentations, people mentioned their own versions of similar ideas with fairly drastically different results. For instance, so Dan, you want to comment a little bit about your aggressive board evaluation function? You used the ratio idea there.
Right.
And it sounded like you had better results than Innocent did with it.
Yeah, I would be curious, looking at it the way that I did it, I implemented it where it had some if-ends. It was, at first it used the prefer kings, so just give 10% weight to kings, essentially, so it wouldn't stupidly give up kings as long as the board was even. And then if the board was not even, it took your pieces plus 10% kings over their key pieces plus 10% of their kings, and it made it positive for you and negative for them. So that, because a ratio of like 6 to 5, you're, as opposed to 5/4, 5/4 is increased, so that both of you losing one piece makes the ratio bigger and encourages it to go ahead. But it only did that when it wasn't even, and I made sure to make it go negative with the others. And it couldn't ever have a zero denominator, because the only time that could ever happen is if the opponent had 0 pieces, in which case you've won the game.
Right.
And it would have already checked for game win, and it would have never got to the valuation function. So something was different there. I don't know.
Yeah. From what he's described, what do you think was different?
I think mine was way more simpler than that. I basically took the pieces of the current player divided the pieces of the other player. And in that situation, I think it's possible for the other player to not have any pieces, which would lead to 0 and then make the program crash. I kind of abandoned it when that happened. I played with it, but when I ran the tournament, it crashed somewhere within some games.
So another contrast was Silas. I think I remember you saying you had a board evaluation function that liked the center, right? And then one of you guys had one that did that, where you tried that and it didn't work well. Okay. So Silas, why don't you give a little more detail about what it meant to prefer the center in your game?
Basically, I just gave additional, for the columns, I did the columns and rows all the way across the middle 2, or the middle 2 ones. And I just added a weight to, if you had a checker piece on your, if you're, like, say you're playing, if you're black, if the black checker had a checker in those 2 rows, that checker got an additional weight. So that kind of helped pursue them to the middle.
So Caleb, what was your implementation like?
I did the similar. Did you use that with something else?
I used it with the Kings as well. That's probably why it actually did better.
But mine was similar to that, except it wasn't just the rows. It was actually a square in the middle. It was 4 wide on the rows and 2. It was 4 tall on the column. No, columns were 4 wide, and it was 4 of the rows. So it was basically the middle square. It gave more weight to those, the more pieces they wanted to have at that location. So I think his kings probably is the reason.
Yeah. Very interesting. Very interesting. It sounds like the general subjective experiences of playing it were, once you cranked it up enough, it was just over. That seems to be what I'm hearing. Yeah. So this is pretty interesting, right? And I mean, this is a pretty quirky set of algorithms, but they're not all that complicated in the end. And it can be astonishingly effective. Let's talk a little bit about what Kate and Eric were just mentioning about, well, once you've got this, like, what's the point of a human player? And I'm going to talk a little bit about, what the current status is in the chess community, where humans can't beat the best chess computers at this point. But what chess players, but the game remains quite vibrant and popular to play. Actually, last weekend, I ran a chess tournament right here at Hendrix for high school kids. That was totally random. Someone from Conway High contacted someone at Hendrix wondering if they could use Warsham. Then that person thought, maybe whoever in charge of math and computer science might know of somebody who can run a chess tournament. And so he asked, would it be you or anybody else? I was like, yeah, I can run a chess tournament. Yeah. And so we had a great day of it. What happens, right, is you go into the tournament and there's a notation for writing down your game so you can kind of go back and review it. And the beauty of a chess computer is you can enter your game into the computer, and at each move, it'll run its search algorithm and kind of tell you how you were doing and where your mistakes were, which winds up really having a lot of utility. So even though something like checkers, so checkers is in a different category than chess. Checkers is absolutely solved. And the solution is basically the endgame database is so big that an optimized alpha beta can just reach the solved endgame database. And bam, there we are. Chess is not in that situation. Chess is not solved, but no humans can beat the best chess computers at this point. Just can't be done. But in any event, you get the computer to evaluate your game, and it starts pointing out, okay, yeah, this is kind of where you screwed up as you're going through it, which can be pretty informed. There's something else that's become popular in the chess community, which is actually kind of surreal, which is they're starting to have tournaments where it's a team game. So a team of humans against another team of humans with arbitrary computer help allowed. Explicitly allowed. So you look at the current position, you fire up some chess engine. It makes certain recommendations based on different alternatives that you try. So basically everybody is supercharged by like 8 levels of alpha beta or what have you as they charge ahead. Another completely solved game is Connect 4. As it happens, Dr. Yorgi is a pretty big Connect 4 fan. He really likes playing it. And he has an entire book on Connect 4. And in the book, it discusses various positions and situations and the like. And whenever it discusses them, it then says, in this situation, you absolutely do this. Why? Because it's completely solved. And the engine tells you, in this situation, this is the best move, because it's able to search to the end. Othello is also very alpha beta-able. It's a fairly brutal game for that. It was only in recent years that the great granddaddy of board games really started to fall to the computer, and that's Go. Go is rough because Go has a 19 by 19 board in which every position is a legal move. So if chess has a branching factor of 20 or 30, Go has a branching factor of 361. Right. So alpha beta search has proven not useful for Go. Ultimately, the solutions to Go involved using what's called a Monte Carlo tree search. And so the idea of the Monte Carlo tree search is you effectively play massive numbers of completely random games. And for each position, you start accumulating counts of, when I pass through that position, do I ultimately win or do I ultimately lose? So with Go, that was combined with some machine learning algorithms to do some pattern recognition. And that's sort of where the AlphaGo thing came from. And now that has become difficult for humans to defeat. But it kind of took innovation in computer gaming to a new level. The combination of the Monte Carlo tree search and the machine learning algorithms is really what got that to a really cool place. All of that said, you know, it was in the 1990s that Garry Kasparov was, you know, the first world champion to be definitively defeated by a computer. And it was sort of an epochal event. Like, you know, up to that point, sort of normal players like me or whatever, if it was on a low setting, which as you all now know means what is the depth of your alpha beta? Like, so at that time, you know, you would pick, you know, what difficulty do you want? 1 through 8. And it's just all about how deep does your alpha beta go. But you know, see, the algorithm was really almost that transparent. So, you know, I could win against a 3 or a 4 maybe, and then beyond that, you know, it was over. Kasparov was still competitive against a machine that contained databases of every game Kasparov had ever publicly played. Not to mention many, many, many other grandmasters. So what they did was they built just a monstrous chess database in which, if it reached a position that happened in a known game, and this is, you know, loaded up with grandmaster games especially, it would follow up, well, what did the old grandmaster do to get to the win? So it's like he's playing against this unstoppable machine with instant database access to all of this stuff, you know, with alpha beta piled on top of that, right? And he was still actually competitive into the late 90s. I mean, the dude is amazing. Well, this gets into a deeper issue about all of this. Computer gaming, strategy gaming, was a very early target for AI research, as we discussed, right? You know, this is stuff that was begun in the 50s. Intuitively, why do you all think that is?
Rules?
It had rules, and so elaborate, please.
Rules are very conducive with computer science music.
They are, right, so you had a constrained domain. Yeah, good. Spencer, what were you going to add?
I was going to say war, because
Mhm.
1950s is definitely around end of World War II, start of Cold War era.
That was in World War II, the Enigma. That was a code-breaking machine. So I guess part of what you're getting at is imagining people saying, well, if we come up with an AI that wins checkers, maybe we can come up with an AI that beats the Russians.
Sounds like something. Sounds like that.
Yeah. Well, let's just say that military funding for AI is kind of a thing. Anyway, yeah, there's a lot of military-industrial complex here. Why else? Why else do you all think these kinds of games would have been an appealing early target for AI? Yeah.
There is a limit to the number of possible things that can happen. There is a limit to the number of possible configurations of a game. So if you can exhaust it, you can perhaps master every bit of thing that is needed to win. So,
Perhaps. Yeah, Silas.
I just think that's do it. It's, they're predictable. Like if you run it enough times, you can eventually guess what someone's doing.
Yeah.
And also, it's a sufficiently complicated enough task that it's impressive if you can get a computer to do it better than you. I mean,
That's the real kicker, right? For, you know, generations, one of the indicators of saying, oh, this person's really, really smart is that they could perform well in a tabletop board game. And games like chess and checkers and Othello and others have the added appeal of no luck. These are games of pure strategy, right? There's no luck factor at all. And so it was seen as, well, if we can figure out what it would mean for a computer to be really, really good at chess, maybe we figured out something important about what it means for a machine to be intelligent, generally speaking. When you all were playing it, did you feel like there was like an opponent there, like a sense of a presence?
yeah.
I mean, you know it's a psychological trick. You know, especially if you've taken computing organization, you know there's no there. Deep down, right? It's just a bunch of electrons jumping around, right? There isn't a there. But boy, it feels like it, doesn't it? I mean, it's this, you know, it's almost creepy. How does it know what I'm doing?
Yeah, when you think you're doing good and then it like gets you, like that just kind of like makes you feel like there's somebody back there.
Yeah.
There's a time like my pieces and the AI pieces sort of distributed somewhere.
Yeah.
I'm like, I'm gonna take this piece, move it back and forth, just back and forth to see what it's gonna do. You know what happened? It also kept on moving its back and forth until I did something different. Then I also did something different. I'm like, whoa, that's creepy. Yeah, it was weird.
Yeah. And part of what's really funny about this, right, is you were the creator of it. You know everything in it because you put it there. And yet you're still having these experiences, you know? So it's part of what I think continues to intrigue people about this concept of the AI board game player. So all of that said, what has this taught us about AI, what it is, what is missing from it to be something that would be a little more AI-y? Thoughts? Yeah,
I mean, you know, when you play a game, there's like when you play a game against an actual intelligent, like, right? You know, humans usually.
Yeah.
Humans
are usually intelligent.
Yeah, they're the life we're referring to usually when we're playing games.
Yeah.
You know, there's more to a game as far as like you communicate, and there's like, I guess. And then intelligent-wise, outside of game, there's just more complexity to even just like simple human things than just like the board game itself. So yeah.
Yeah, fish.
Cheating.
Did your game cheat?
No.
Okay.
And, you know, to make it more AI-y, I think it should.
Okay.
You should try it.
Yeah.
How would it?
Yeah. Jay,
Or is like making it more human, you should throw in a little text box so the AI can trash talk.
What are we doing, chat box?
Yeah, that's the last project. Yeah.
The one weakness that I actually saw in this thing, I was playing it, I could do up to like 13 moves pretty adequately on the quiescent, and it would just crush me in the early game. But at the end game, I noticed it was interesting that it would suddenly become stupid. That it would see, it would have a piece that it had, you can just move this thing all the way across the board and get like 5 kings because you've got 5 pieces and I've just got 1 over here. And it wouldn't think to do it because the number of steps that would take would be more than 13. So at the end of it, something that would be easy for a human to see became hard for a computer to see just because the computer was just thinking in terms of number of steps.
Right. Right. And that's where those endgame databases proved decisive in bringing checkers to the state of being a solved game. I mean, it's sort of funny to me that checkers went from an unsolved to a solved game in the time between when I first assigned this project and now. Yeah. I find that kind of unsettling. Yeah, I first assigned this project in spring 2004. So 16 years ago, which was my second year at Hendrix, actually. So yeah, you can now figure out this is my 18th year at Hendrix, but anyway. But in terms of thinking about AI in a broad way, what are some key missing competencies here? You know, what do you want AI to be able to do?
One thing I was thinking about also, like we want AI to be able to drive cars, but the number of possibilities for an AI to have to evaluate driving a car is so much broader than anything else. I mean, it's just, we're so far off from that. But we want it to be able to see new things and bring those within the realm of things it can deal with and which is way off from that.
David.
I think the lack of ability to seek out choices. Because whenever you make an AI, even a car AI, someone had to think, okay, what are all of the possible things that this thing needs to know about? But it doesn't have the ability to be able to then search for those other things that it can then need to be smarter.
Right. Yeah, Eric.
I think that the input should be much more like unstructured than it is currently. Because right now we just give it like a game board and there's no information other than that. But like in the case of like cars, it has to do a whole lot of image detection and like cutting up what section of the thing that I see is what.
Yeah.
You know, so it has to like draw conclusions as opposed to literally just saying, I know exactly this set of things.
Yes.
Also, maybe giving it another bit of rationality in terms of what it's interacting with. Let's say, for example, in terms of chess, usually when I play checkers with like my younger brother, I go easy because him and I we have the same type of thinking. But if I'm playing against like other like really like grown-up intelligent person,
Yeah.
I go hard. Maybe AI could be able to look at someone is playing with like, okay, that's a kid. Maybe kind of go easy. And if that's an adult, maybe kind of go hard. And if something goes with like self-driving cars or stuff like that, you should be able to see, okay, this is a child or an adult, and then sort of put that into consideration. But for now, the kind of thing is most of the time that you still compute all different possible options and you go with the best without caring about the context in which the action is going to
Right.
take place.
Yeah. So this will amuse you then. About 10 years ago, there was a student in this who took a prior version of this course who was deeply, deeply intrigued by this project and wanted to explore it further for his senior thesis. Like, okay, well, we'll advise a project here. And so what he did was he tried to come up with a system where it would automatically figure out how good you were and lower or raise the alpha beta search depth accordingly. So you would play games against it, and if it won against you at a given depth, next time it would play at a lower depth, and so forth. Now, what happened was it got to a point where it basically had this extremely boring outcome where it would just bop between a level at which it would always beat you and a level at which you would always beat it. So we kicked around an idea like, well, what if you had like a fractional notion and then maybe move to move, there was like a probability that it would go a level deeper or whatever. I never really followed up on that though. But yeah, he set up a website and people came and played it and it maintained records about them and all kinds of stuff. So that it starts to get at a little bit of what you're getting at in that we're setting up a context, and this is actually something fairly useful, right? You want to get better and better at the game, and you want a challenging opponent, right? You know, because at some point, sure, you've got your checkers set up, and its alpha beta goes to 12, and its quiescent destroys you, and you play it once, and you're like, well, you know, yeah, that was awesome. It destroyed me, and you've got no incentive to ever play it again because it's just so much better. But on the other hand, kind of like some of you all were talking about, there's no context here, right? Again, the human supplied the context. So Silas, I saw your hand was up.
No. I guess for context, like in the sense that there's like the driving car dilemma, with like not being able to protect like the dilemma between going into a wall or running over someone in the street. Like there's dilemmas like that. Like how is a computer supposed to be able to ever morally decide that?
Yeah, fish.
Back to my idea of cheating. But I mean, AI needs to know when to break the rules. So, like in our useful self-driving analogy, a lot of times I see in like construction zones, there are lots of different like faded lines. Sometimes they don't draw the right lines, and sometimes you have to turn on a double yellow because they just made that new road, but they haven't changed the lines yet. And so, like, knowing when to break the rules.
Yeah, Austin.
And that's really hard because, like, what are the rules for breaking the rules, right? Because, you know, you gotta. You know, because there are times when we know we can all agree that we have to break a rule, but we also have some sort of rule for why we do that.
No police friend.
Because we have some sort of ethical idea of what we're supposed to be doing, and then we also have like this deeper ethical idea of like if things get this bad, then we have to do something else, and we're okay with that.
Then the human drives it.
The philosophy minor is bringing it on.
That's actually like something that's come up in like, or like that is like a big problem for like self-driving cars. Is it's like if somebody on the street like stops in front of you, but if it's like a UPS truck and they're delivering a package for like 10 minutes, like the self-driving car doesn't pass it because it's not supposed to. But like if a human was inside that self-driving car, they'd probably get quite upset about that.
So Dan and I'm going to give you all some closing thoughts.
One thing that what Innocent said made me think, it kind of sounded like he wants the computer to show compassion, you know, for the person.
Yeah. Here's the thing. Yeah.
Is that what we want the computer to be was a sociopath? Because the computer's not going to feel emotions, but if it pretends, you know, because sociopaths can be very good at pretending like they have empathy. and so if you could program a computer to behave as though it had empathy. And so your ideal would be to make a high-functioning sociopath computer.
I mean, right. I have no moral problem with a high-functioning sociopath. Right. If such an individual lacks empathy but decides to live a life as if they had it, you know, there's no moral.
Yeah, they're following the rules, but they're not ever going to choose to break them.
Right.
Yeah.
But with the self-driving cars, I got to tell you all about a talk I saw at a conference this past May. So I was at an AI conference in May, and one of the guest speakers was the head of Nissan self-driving cars. And he basically kicked it off by saying, yeah, fully autonomous self-driving cars, not going to happen anytime soon. So here's what we're going to try. And he described the system they're putting together to have remote human backups for their self-driving cars. And it was getting at a lot of the situations you all were just talking about, like the UPS truck and the faded yellow lines and so on. So the idea was the AI has some notion of when it's out of its depth. So then it signals the human for help. This remote human operator sees the situation and then remotely pilots the car until the situation is evaded. The canonical example he was using was road construction, where you have to then go into the oncoming lane because it's blocked. But it would also apply to stuff like the UPS truck and so forth. Most of the people I talked to at the conference thought the entire scheme was nuts. And there were some reasons for this. One is that he was talking about how they were trying to research how to make this cost effective. That is, if you had too many humans per car, then there's no point because it costs too much money to pay the humans. But then if you've got too few, I can't even imagine the level of stress-inducing, anxiety-inducing, mental health-threatening level of job this would be. Oh, we're not even getting started on that. But yeah, you know, and a lot of it is any engine like an AI engine like this relies on some means of formalizing the noisy data into the world into a nice, neat, symbolic representation. And this is going to be a continuous tension that we see throughout the course. That said, starting this coming week, we're going to transition our point of view. Instead of in a top-down way, thinking logically and symbolically, we're going to start looking at bottom-up, given data, how do you find something symbolic in it? In other words, we're going to begin a unit on machine learning algorithms. And we're going to spend quite a bit of time on them, actually. And what we'll do next week is we're going to start with two that are just extremely simple to implement, simple to understand, and we're going to see how far we can get with them. And we'll be studying a neat problem involving data from Twitter. So look forward to seeing you all on Tuesday. We'll start going over it then. Have a great weekend.